6A. The History of Dynamics. 6.1. Early Greek Theories. The philosophers of Aristotle's day believed that objects could exhibit two types of motion, natural and unnatural. Natural motion was thought to be caused by some internal quality of an object that made it seek a certain preferred position without any application of force. For example, heated air rises, so its natural motion would be rising. Rocks fall, therefore, their natural motion would be falling. In this scheme of the universe, natural motions were sought to allow objects to reach their natural place, or place of rest. For heated air, the natural place was the heavens. For rocks, the natural place was the center of the earth. All motion other than natural motion was called unnatural motion, and was thought to require applied force to be sustained. Natural motions were divided into two subcategories: terrestrial motions, motions near the earth, and celestial motions, the motions of planets. This division of motions arose from the pagan Greeks' dualistic view of nature. The dualistic universe is divided into the celestial and the mundane, the divine and the mortal, the perfect and the imperfect. Celestial motions were thought to be purely circular. They represented the untouchable perfection of the celestial realm that was ruled by mathematics and pure reason. Terrestrial motion included all other forms of natural and unnatural motion. These two types of motion were considered to be completely separate and unrelated. This division helped to explain how heavenly bodies automatically moved in perfect circular paths. According to Aristotle, an object's heaviness determined how vigorously it sought its natural place. A heavy object would move more vigorously toward the surface of the earth than a light object. Conversely, an object's vigorousness would measure its heaviness. Were these conclusions supported by experience? It seemed so at the time. Remember that Greek philosophy placed deductive reasoning on a qualitatively higher plane than experimentation. Even if experimental data contradicted a belief derived from reasoning, one could say that the experiment itself was faulty, since it was subject to the presupposed corruption of the material world. 6.2. Galileo's Investigations. Galileo chose a different perspective from which to study the problem of motion. His first task was to collect facts and establish an accurate description of motion. This description is known as kinematics. From this foundation, he inductively developed workable theories of dynamics. No scientist uses a strictly deductive approach in his work. Suppose a feather, a tennis ball, a baseball, and a bowling ball were dropped from the top of a 30-meter tower. How long would each object fall? Obviously, the bowling ball would hit the ground first, but why? If Aristotle's concept is correct, it is because heavier objects seek their natural positions near the center of the earth more vigorously than do lighter objects. Extending this logic, the speed of each object should be determined by its mass. The baseball, which has more than twice the mass of the tennis ball, should fall at least twice as fast. The bowling ball, about 50 times more massive, should fall 50 times as fast. Table 6-1 records the actual time required for each object to fall. Notice that the heavier objects fall at nearly the same rate. After a certain density is reached, the heaviness of the object has little effect. In this respect, Aristotle's theory of natural motions was shown to be wrong. If a wind should blow during the experiment, the feather would be blown off course, and its falling time would be greatly increased. The falling times of the other objects would also be affected, but not as much as the feathers. Apparently, the presence of air has a great effect on the rate at which objects, especially light objects, fall. Astronauts have performed experiments to test this conclusion. Colonel David Scott dropped a hammer and a feather in the vacuum at the moon's surface during the Apollo 15 mission in 1971. Without the presence of air, both objects fell at the same rate and hit the ground at the same time. Even though Galileo could not perform this experiment, he reached the same conclusion by considering the effects of air resistance on falling objects. Aristotle believed that unnatural motions could only be maintained by the continuous application of force. Suppose you slide a large box of books from the foot of your bed into your closet. From experience, you know that when you stop pushing, the box stops almost immediately. This observation seems to show that Aristotle was correct. Do other observations confirm this conclusion? Consider the flight of an arrow. The arrow begins to move when the bowstring applies a substantial amount of force, yet the arrow still moves after it leaves the bow. According to Aristotle, some force must continue to push the arrow, or it will stop and fall to the ground. Where can the force come from? Aristotle said that the air separates in front of the arrow, allowing the arrow to pass through easily. In the wake of the arrow, he said, the air snaps closed and provides the force to keep the arrow moving. To disprove Aristotle's explanation, you would need to perform this experiment in a vacuum. If air provides the force to sustain the arrow's motion, the arrow should immediately cease moving if released in a vacuum. Instead, it continues on almost the same path as before. Since Aristotle was committed to his theory, he had to endow the air with special, unobservable properties to account for the arrow's motion. This kind of hypothesis, based on conjecture rather than observation, is called an ad hoc hypothesis. Aristotle's explanation was a direct consequence of the Greek philosopher's erroneous belief that inert matter had attributes similar to those of conscious organisms. 6.3. The Principle of Inertia. Galileo studied unnatural motion with an experiment similar to the following. Suppose that an unpolished metal cube rests on a wooden plane. If you give the cube a push, it soon stops moving. If the cube is polished and the plane is changed to oiled, polished metal, the cube travels a greater distance. Theoretically, if the cube and the plane were totally frictionless, the cube could slide forever without slowing down. Now, suppose you arrange a frictionless, flexible, U-shaped strip of material, as in Figure 6-4. This strip acts as a track for a frictionless ball. If you release the ball at the top of the track at the left end, the bale accelerates down the incline, rolls along the bottom of the curve, and then encounters a rising incline. The ball slows down as it rolls up the incline and stops when it reaches its original height. The reason this occurs will be considered in Chapter 9. What happens if the slope of the right end of the track is decreased and the experiment is performed again? The ball again decelerates up the right-hand incline, but its deceleration is less than before. It continues moving until it reaches its original height, although it has to move farther horizontally to reach that height. If the right-hand end of the track were bent to be completely horizontal, the ball would not experience any deceleration. It would naturally continue at a constant velocity for an indefinite amount of time and distance. From such concepts, Galileo inductively asserted that the natural state of motion of an object could include moving as well as resting. Galileo's principle of inertia states that an object will continue in its original state of motion unless some outside agent acts on it. A moving object does not require a continuous push to maintain a constant velocity. In fact, just the opposite is true. A push causes a change in an object's state of motion. This conclusion was truly amazing considering the limitations of the experimental apparatus of the time. The concept of inertia has served as the cornerstone of dynamics ever since Galileo. 6.4. Sir Isaac Newton. Newton carried forward the conceptual investigations of Galileo. By the time he was able to devote his considerable powers of deduction to the problem, much information about the movement of planets had been documented by the great astronomer Tycho Brahe, and Johannes Kepler had formulated his 3 laws of celestial mechanics. See Chapter 7. Newton gave credit to these and other scientists who had gone before him for preparing the way for his discoveries. Newton's work grew from his study of gravitational attraction between astronomical bodies using differential calculus, which he had developed for the purpose. Eventually, he published his findings, which included his 3 laws of motion that define the concepts of force, rather than an unspecified agent, mass, and momentum, in his famous work Principia, short for Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy. Newtonian dynamics has been validated repeatedly for ordinary objects over the 3 centuries since Principia. Only within the last century have scientists discovered that Newtonian physics does not hold true for particles that are extremely tiny, subatomic sized. and or moving extremely fast, moving at a significant fraction of the speed of light.